The boundedness property then, let f be continuous on the interval ab, then f is bounded on ab, and we're going to look at proving part 2 now. We've just proved part 1. F attains both a maximum value and a minimum value somewhere on ab. So let's have a look at part 2 then. Here it is here. So let A, capital A, equal this set here, f of the entire set AB, all the f of x's, for x varying between A and B. Since f is bounded on AB by part 1, wasn't it? A is bounded both above and below, so this set is bounded above and below. So it'll have an infimum and a supremum. So let the M be the infimum, the capital M be the supremum of the set A. What is now required is to show that there exists an M and M, both values of the function f. So yeah, these values that already exist, we can find values a c and a d probably, such that f of c is m and f of d, say, is the capital M. So, to this end, suppose by way of contradiction that there is no value of x for which f of x equals m. Right, so there's no value of x for which f of x equals m. So we're looking at the bigger one of the two in this part of the proof. Define a new function g by g of x is equal to this for all x in AB. So g is defined on AB and continuous on AB. So, and it says by the sum product and reciprocal rules. So it's defined because the denominator is non-zero, because f of x never equals m, because there's no value of x such that that's the case. So this is non-zero. Both constituents m and f of x are continuous, so this entire sum, m minus f of x, is continuous. The 1 is a continuous function, so again the quotient rule here for continuous functions, g of x is a continuous function. So g is a continuous function defined on AB, and as such by part 1 g must also be bounded on AB. So if it's bounded, there's going to exist a real number k greater than 0, such that g of x has that upper bound. G of x is less than or equal to k for all x in AB. So what does that mean then? Well, let's have a look. G of x can be replaced by this. It's less than or equal to k. Now this is positive, as we said before, because this is a bigger value. It's the uppermost value, it's the supremum, but there's no value where it's equal. So this is always greater than 0. So we can move that up there in the inequality, and we don't have to flip the inequality. K is positive, so at the same time we can move that down, and the inequality is still preserved. So we've done that there, and then we can move the f of x, flip the sign as we move it across, the equals, and the 1 over k we can move over here, and we end up with this line here. So this is now saying that f of x is bounded above by m minus 1 over k for any x belonging to AB. But this tells us that this is an upper bound. But this upper bound is smaller than the supremum, which is m, which is the least upper bound. Because capital M is the least upper bound, isn't it? So that's a contradiction. So the assumption that we here assume for contradiction, there is no value of x for which f of x equals capital M, is false. So in other words, there must be a value of x such that f of x equals m. So you could say there's a d in AB such that f of d equals capital M. So f attains then a maximum value somewhere on AB. A similar argument shows that f attains a minimum value somewhere on AB, and we'll look at that in the next and final part of the proof.